Okay, so let's say we are dealing with interstitial diffusion, the diffusion of carbon within ion. Let's say the atom is initially at this location. Okay, and then it jumps interstitial. It's jumping from its original location to the neighboring vacant interstitial site and randomly continue, right? Let's say it jumps for n steps. R1, the first jump, randomly. R2, of course, I'm just illustrating. You can draw your own. It may look different, right? R3, blah, 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 and finally to Rn. It jumped for n steps, n jumps, okay? And after n jumps, the total displacement vector. Each of the jump, it has distance, it also has direction, right? So the total displacement would be a vector from the original position to the final. This one we call it Rn. This would be a vector, has certain length, has certain direction, right? Points to a certain direction. Okay. And do you see that mathematically, Rn in terms of vector would be just the addition of the individual vector. R1 first jump, R2 second jump, R3 third jump, blah 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 to Rn. All those n jumps. And mathematically we rewrite that thing as Ri, I from 1 all the way to n. Okay, mathematically. And I put a arrow here means each of the jump is a vector, right? Of course, within simple cubic, there may be certain restriction about the way they jump, but still it's a vector. Okay, and to get a so-called absolute displacement, which means we want to go from a vector to the scalar, to the corresponding scalar after n jumps, and mathematically what you learned would be this, right? A vector dot product itself, we get a scalar which is square term of the length. Make sense? This one would be the vector Rn from here to here. Dot product itself would be, we rewrite Rn as the summation of the individual jump steps, right? Of course, each of these are still vectors, and we have dot product in between. And mathematically, we can further expand. That's what you learned in linear algebra, okay? From I all the way to n. From I all the way to n. We write it as a summation of all these terms. The first terms are Ri times Ri. That will be the so-called square term, right? R1 times R1, R2 times R2, R3 times R3, and dot product. And then we have the so-called crossing terms. R1 times R2, R1 times R3. Look at here. The first term is always what? R1. And then the second term is from which one? Plus I. 1 plus I from 1, which means the smallest one would be R2, go all the way to n minus 1. Okay, when I equals n minus 1 plus 1, we got what? When I equals n minus 1 plus this one, Rn, right? This whole thing just means from R1 times R2 plus R1 times R3, R1 all the way times Rn, right? Of course, this is still dot product of two vectors, and we put 2 here. Why? Remember when you do these types of expansion, there's A1 times B1 and there's B1 times A1, and then of course you have to combine these. That's where the 2 terms come from. Or put another way, that's R1 times R2, that's also R2 times R1, and you combine these two. And R2 times R1 would equal to dot product R1 times R2. Make sense? So that's the crossing term. And the second one would start from, the first term is always R2, go all the way to Rn. Third term, go all the way until the last one. Rn minus 1 times Rn minus 1 plus I, from 1 to 1. Make sense? All these are so-called crossing terms. The first would be the square terms. Okay, those people are really smart who came up with this. And mathematically, we can rewrite again I vector become Ri square. Do you see that? From vector now to scalar, because it's the same vector you are doing the dot product of itself. Ri is just the length of that vector. Now we go from vector to the scalar because it's dot product of itself. And then similar for here, we just from one summation to two summation. The first Rj now is from R1 all the way to n minus 1. J is from 1 all the way to n minus 1 times the other one, j plus I. It's the second term, 2 plus I, 1 plus I, j plus I, and j and I from n I1 all the way to n minus j. That's the crossing term. Okay, of course, Rj and Rj plus I, typically these two would not be the same. So that's why I still cannot, I still have to keep the vector symbol. Okay? Let me just double check. Again, this is what we have from previous slide. Rn times Rn, that's our net total displacement after n jumps. And we did the dot product for the same vector equals the square term, which now we changed from the vector dot product to just the scalar square, time plus this cross term. The cross term between the number j jump and the number j plus I jump. The two vector dot product. And mathematically, if we think for all these jumps from 1 all the way to n, for each of the jump, if it's, remember, it's interstitial jumping. The distance for each of these jumps should be the same length, right? Because we assume simple, let's say simple cubic lattice structure. Okay, so each of the jump, its absolute value for that vector, for all of those individual jump, let's call it alpha. Make sense? And they should all be the same for the same lattice, for the same interstitial. As a result, if we say alpha is the jumping distance, as what we said before, jumping distance for interstitial jump to its always nearest neighbor, right? It always can jump only, most likely, only to its nearest weakened interstitial side, not to the second nearest. Make sense? Can it jump to the second nearest? In principle, it can, but the probability of that is extremely, extremely low. Make sense? Okay. So now what you learned in, I guess, linear algebra, Rj vector times Rj plus I vector. Do you see that these two vectors have the same absolute value? I can write it as alpha square times cosine term. What is that cosine theta? 2 vector, right? That cosine theta is just the angle between the two vector. That's what you learned, right? This theta j, comma, j plus I is just that angle between these two vector. Okay, and we got that cosine term. So as a result, the displacement after n jumps, the displacement after n jumps would be, okay, r square, the same, right? Its dot product for itself would be Rn square from vector to the scalar square, because for the same Rn, first term is alpha square times n, right? Because from from 1 all the way to n, it's the same, right? Alpha square times n, and then 2 alpha square j plus I become alpha square, and the cosine theta, of course, we have this double summation. We still keep this double summation. Okay? Right? This is how we go from dot product of vectors to square term of these. Okay. Now let's consider Are we considering only one atom jump? No. In the end, in the beginning we said, okay, one atom jump of how many steps? N steps. But in overall, we are considering, quite often, we are only concerned with average jump over a large number of atoms. Make sense? In the end, I'm not concerned with only one atom. I'm concerned with the average effect over a large number of atoms. Okay? And each atom, for simplicity, of course, each atom may jump different times. But let's, for simplicity, assume each atom's on average jumped for, as my considered, n times. Over a large number of atoms, some atoms may jump a little bit more than this n times. Some may be jumping a little bit less. But let's say on average they jump n times. Make sense? So, as a result, the so-called average displacement, average of this Rn square, average, which means what are we going to get? We're going to get Rn square, but we are going to put a bar on top for average. Rn square means what? For one individual atom jumping after n times, but then we do a average. We're counting a billion or a zillion atoms. Each atom would jump, but let's count an average over them all. Do you see the first term still got kept? We make, for simplicity, we assume on average each of them jump how many times? Still n times, right? Because some may jump more, some may jump less, but on average each jumps roughly n times. So the first term got this one. The second term, 2 alpha square, we put the average sign above here because the alpha term would be constant for a fixed lattice, right? So that's what we have. The average jumping distance squared would be this. Okay? Now we are going to do some assumptions again. We say over large, you said, okay, large number of atoms, not 10, not a million, zillions, really, really high number. The average cosine term, now we are kind of only hand waving, should be this. Does this make sense? Jump, jump. The angle between arbitrary two number of the jump, and then I'm doing that for one atom, and the overall for all the atom doing average. This is not a rigorous mathematical proof. You see my point? It's not a rigorous mathematical proof, but you can kind of understand it because in the end, does this piece of material go away by itself when you consider the jumping of atom within it? This whole thing doesn't move away, right? So kind of you can understand, okay, when I do this average over a large number of atoms, this cosine term, what is that cosine? Between the two jumps that I chose, that cosine term, I added up, average over all the atoms come down to 0. This is a hand waving explanation, not a mathematical proof. You understand what I mean? This is for model simplicity. If we accept this, then what do we get? Remember, we are concerned with the displacement squared, but average. This whole thing, displacement squared average, would be the first square term times the cosine term average. But because we said over a large number of atoms, the cosine terms goes to 0, which we said it's only an explanation, we accept it or assumed it. This is what we're going to have, right? What does that mean? The average square of the displacement is n times alpha square. What does alpha mean? Each step, the jumping distance. It's a scalar, and quite often you know it based on the lattice structure. Make sense? What does n mean? The number of jumps, depending on what's the n you select. Okay, and quite often a high number. And if we still remember define when we were doing the interstitial diffusion, we introduced the concept of gamma. What does gamma mean? The so-called successful jumping frequency. Within 1 second, how many successful jump? If we define gamma, and then if the n jumps take a total time t, if the n jumps take a total time of t, right? Each jump will take some time. The n jump will take time t. What's the relationship between gamma and the n and the t? What's the relationship between gamma and n and t? It should be a very simple relationship, right? The total number of jumps, n, would be how frequently you jump, successful jump, times how long you are thinking, right? If I'm thinking 1 second, my total jump is 1 second just times this frequency, successful jumping frequency. That gives my total number. Make sense? You see that? That relates the n, how many jumps, and the time t with the jumping frequency, so-called successful jumping frequency. And if this is what we have, n is gamma t. If this is what we have, again, Rn squared average is n alpha squared. Now we are going to rewrite n as what? Gamma t times alpha squared, right? We're going to rewrite n as gamma t times alpha squared. And we rearrange. Put alpha squared and gamma together. Put alpha squared and gamma together. This is our displacement squared average becomes gamma, how frequently a successful jump times the distance for one jump times t. Okay, this is what we have. And then from earlier, if we said earlier interstitial diffusion, we said, okay, for interstitial diffusion, the diffusion coefficient, remember we mentioned something like this. The diffusion coefficient is actually a function of successful jumping frequency and jumping distance, right? The diffusion coefficient is these two. Where does the 1/6 come from? The direction, right? The direction, okay. As a result, how are you going to rewrite this gamma times alpha square? It equals what? 6 times d, right? This gamma times alpha square is just the 6 times of the diffusion coefficient. Make sense? And as a result, do you see this alpha square average would equals to what? This this Rn square average would equals to 6 times d times t, right? This is what we're gonna have. And of course, we have the average term. It's a square term. 6 times dbt, kind of. It's not a strict root. It's what we call a root mean square average. I took a square root of the left side, would get a square root of 6 times dt, right? Which means this guy, the average, and then I take a square root, is roughly 2.4 times square root of dt. Again, what does t mean? Time, right? How long time? Of course, it's jumping. This time t gives us n jumps. Okay. What does dB mean? That's our diffusion coefficient. In this case, in particular, interstitial diffusion coefficient. We said, okay, what does Rn mean? The net displacement. What does Rn square mean? The square term of that displacement, which is a scalar, and you do average, and then they take square root. That's called a root mean square, right? Root, square root, mean. You average of what? Of all the square terms. Root mean square is roughly 2.4 times square root of dt. What does this mean? Kind of remember, what does Rn mean? The vector going from the original location to its final location. And when you do this over a large number of items, you find out this value is now 0. As time goes on, this value goes, as t increase, this value goes higher and higher. Make sense? Which means if you look at any atom on average after time t, they are not sitting at the same location. They are going to be some distance away from its original location. Make sense? And how far is away from its original location depends on time t and the coefficient of diffusion. The longer you wait, the further it's wandering away. The faster the diffusion coefficient, the further it's away. Make sense? But it's not at the same location. That's very important. When we think, okay, even the same atom is wandering around, over time, it doesn't come back to the same location. Over time, each of the atoms would be some distance away from its original location. It's not at its original location, which is very, very, very important. Even though it's kind of similar types of atom, over long time, each of the atom will be away from its original location. It's not sitting at its original location. That's the very important implication. Okay? So we have homework.